Hello, this is Bob Schmidt. This is one of a series of videos on the QC optimization project, or the War on Variation. The War on Variation is a company-wide initiative, so it's important that we have a common language and understanding of quality control. These videos are designed to provide that common understanding. And the objective of this particular video is to introduce the idea of controllability. This series of videos emphasizes three concepts that are fundamental to quality control. They're stability, capability, and controllability. In the last video, we took a detour and discussed power curves, which will be helpful for a discussion of controllability. Let's go back to our high-level diagram. We've covered the blocks there that are shown in white. We're going to look at controllability, the one in blue, and then lastly we'll look at process improvement. So you should have a good understanding of stability and capability and power curves at this point. So going back to the stability, the output from a stable process is common cause variation, and we can use this to evaluate capability. Capability helps us assess the risk when the process is in control. And from that also, we get the size of error that we need to detect to avoid making unacceptable errors. The common cause variation is also used, as we saw in the last video, in power curve analysis. And this tells us the size of the error that we can detect. So controllability is comparing the size of the errors that we must detect to the size of the errors that we can detect in a particular QC program. And we evaluate various QC programs and then compare the costs and pick the most cost-effective plan. So that's just a preview of where we're headed. I've used the term QC plan many times, but I haven't defined it. So what is a QC plan? So that's probably a good place to start. A QC plan has three major components. It has a sample plan, statistics that are calculated from the sample, and a decision rule. Altogether, these compose a QC plan or QC strategy. And remember, the objective of this plan is to detect a shift in the process should one occur. Drilling down, let's look at what goes into a sample plan. Well, the sample plan has three elements. It's the number of control levels that you choose, the number of repeats at each level. In lab medicine, we usually use a single control at each level, but we could certainly use more. And then the frequency of sampling, once a day, every batch, every other batch, and so forth. The point is there's a vast number of possibilities. And this is constrained somewhat by regulatory requirements, but the number of possible plans is still very big. So controls cost money, and so each sampling plan implies some sort of cost associated with that plan. The sampling plan provides raw data, and given that data, we can calculate various statistics which would be plotted on a process behavior chart. We would then monitor these statistics for patterns as the process evolves over time. At ARUP, we typically plot individual values, but we could calculate means, standard deviations, ranges, exponentially weighted moving averages, cumulative sums, and so on. There are about 10 or 15 statistics that are commonly used in quality control. You can also monitor more than one statistic. For example, in other industries, it's very common to calculate the mean and range of repeated controls and monitor these over time. So in that case, you'd monitor two process behavior charts. The point is, there are many options for sample statistics. Finally, we need to select a decision rule. And the decision rule is the criteria we use to determine whether the system is in control or out of control. In a previous video, we used the three standard deviations as a signal of an out-of-control process. The 3SD criteria is widely used, but there's no limit to the criteria you might use. At ARUP, we commonly use Westgard rules, which is a set of about 5 rules. These are standard in the lab industry. The bottom line is that the universe of QC strategies or plans is enormous. You can think of all the combinations of sample plans, sample statistics, and decision rules. In the lab industry, we've tended to converge on a rather narrow set of QC strategies. This may be because they've shown they're the best or because nobody has investigated alternatives. The good news is that QC planning is simple because in practice we only need to compare a few rules given the convergence in the industry. I do wonder whether we can find better rules, and given our volume of testing, even modest improvements in QC performance could be significant. But this is a topic for future research. For now, let's focus on the traditional methods. This slide shows an overview of QC plan evaluation. The QC plan, as we've seen, consists of a sample plan, sample statistics, and a decision rule. The QC plan is evaluated relative to some detection problem. And this is important. The performance of a QC plan depends on what you're trying to detect. Are you most concerned about shifts, If so, are you concerned about detecting large shifts or small shifts? What about trends? And what about changes in random error? Are these transient or long-lasting changes? The point is that QC plans are like tools. You need to pick the right tool for the job. So you can see there's almost an infinite number of detection problems and an infinite number of QC plans that you could test. And clearly this is the path to madness. In the lab industry, we're mostly concerned with shifts because they're believed to be the most common source of error in automatic analyzers. And this is good because it limits the universe of detection problems that we need to investigate. In the lab industry, we generally compare the performance of 5 or so QC plans for detecting shifts of a particular size. The performance of a QC plan is evaluated in terms of risk and cost. With risk, first look at the ability to detect unacceptable results, which is statistical power, and then when the process is in control, we evaluate capability. Then we look at cost, the cost associated with false rejections and the cost of the sampling plan. So let's see how this is done. James Westgard developed a method to determine whether a QC plan can control a testing process. His method's quite clever, and it's based on a graph called the OPSpec chart. The OPSpec chart tells you whether a QC plan can reliably detect an important process shift. In theory, the OPSpec chart could be used to compare any QC plan. In practice, the OPSpec chart is used to compare a limited number of QC plans that are commonly used in clinical laboratories. Let's first look at how OPSpec charts are used, then we'll take a look under the hood and see why they work. So let's just look at what's plotted against what in the OPSpec chart. The OPSpec charts plots the percent allowable imprecision against the percent allowable bias. And the percent allowable bias and allowable imprecision are simply the ratio of your imprecision and bias to the total allowable error. So you see on the horizontal axis, it's just the ratio of the standard deviation to the total allowable error. And on the vertical axis, it's the bias relative to the total error allowable. The plane shows all combinations of bias and imprecision that a process could possibly have. You might call this the operating plane. And you can plot your current state on this graph if you know your imprecision, bias, and total allowable error. And we call that the operating point. Any operating point within the circle has an acceptable error because its combination of imprecision and bias is below the total allowable error. Operating point A is really good. It's well within the total allowable error. Operating point B is near the limit of the total allowable error, and points C, D, and E are operating beyond it. These processes are producing results that could harm patients. C has too much bias, D has too much imprecision, and E has too much of everything. This is the same graph we saw in the previous slide, except that a diagonal line has been added. This diagonal line divides the operating plane into two parts, a controllable region and an uncontrollable region. I'll show you how to find this line in a minute, but for now, all you need to know is that you can find such a line and it's determined by the QC plan. The controllable region is the set of operating points for which the QC plan can reliably detect shifts that could produce serious errors. In a sense, the controllable region represents the points that are safe with respect to a particular QC plan. So what you should take away from this is that every QC plan is associated with a line, like the one shown here, that divides the operating plane into two regions, a controllable region and an uncontrollable region. And the controllable region represents an area that can be operated safely for a particular QC rule. Each QC rule has a controllable region. Any process with an operating point in the controllable region can be safely managed by a rule that covers that region. Let's say the diagonal line is for the 3 standard deviation rule. And the 3 standard deviation rule could control a process at operating point A, but could not control a process with operating point B. That is, using this rule, we can reliably detect shifts that produce serious errors for a process operating at point A, but we couldn't detect shifts that can cause serious error operating at point B. This graph shows the controllable regions for 3 different QC rules and 4 different operating points, A, B, C, and D. So which QC rules can control a process operating at point A? The answer is all of them can. And this point has really good quality, right? It has low bias and low imprecision. A control plan would only have to detect large shifts to prevent unacceptable errors for a process operating at A. Rule 2 can control a process operating at A or B, but could not control a process operating at C or D. We would have to reduce the variation in processes C and D so that they were below the line if we wanted to use Rule 2. Generally, the rule that has a larger controllable region will be more expensive. So in this graph, we can expect Rule 3 to be more expensive than Rule 1. There are exceptions, but this is a pretty good rule of thumb. So the key points are, every QC plan has a controllable region, and every testing process has an operating point based on its imprecision and bias. We can change the operating point by improving the process. A QC plan can control a testing process safely if the operating point is in the controllable region. So we have two key concepts, the operating point, which is a property of a testing process, and the controllable region, which is a property of a QC plan. We have a couple of variables that we can use or manipulate to ensure that a process is controllable. We can choose a different QC plan. For example, suppose our current QC plan was Rule 1 and the testing process was operating at B. We would be in trouble because point B is outside of the controllable region for Rule 1. So what could we do? Well, one option is to choose a rule that can control the process, such as moving to Rule 2 or 3. The other option would be to change the operating point by improving the process. You can see that we can control the process with Rule 1 if we move the operating point from B to A. So given a rule and an operating point, you should understand how to use an OPSpec chart to ensure that your process is controllable. But where do these lines come from, and how do they connect to QC plans? Let's take a look at that next. This slide is from a previous video. It shows how the error budget is consumed by three things: the bias, the buffer, which is Z times S, and any potential shift that might occur. We found the critical shift that we need to detect to prevent serious error from exceeding the maximum error rate. And the critical shift is the size of error that we need to detect. This equation shows that the critical shift is defined by the operating point, the percent allowable bias, and the percent allowable imprecision. So how does this help us? So as we saw in the previous slide, the critical shift, the shift we need to be able to detect to prevent serious errors, depends on the operating point. And also you know that big shifts are easier to detect than small shifts. This is common sense and is a property of any measurement. It's easy to detect whether two people have different heights if they differ by 1 foot, and it's hard to tell if they differ by ½ an inch. The same applies to detecting shifts. It's much easier to detect big shifts. So the principle here is that the size of the shift we need to detect, the critical shift size, needs to be greater than the size of shift we can detect with our QC plan. So put another way, if I can detect a shift of size X with my QC plan, I can control any process that has a critical shift size bigger than X. So how do we find out what a QC plan can detect? The answer is that we get this information about the shift size we can detect using a QC plan from our old friend, the power chart. This slide shows the size of shift that various QC plans can detect with 90% reliability. The vertical axis shows the probability of detection, and the horizontal axis shows various shift sizes. Each curve shows the probability of detecting a shift of a given size. There is a power curve for each QC plan. Hence, each plan varies by the number of repeats on this slide. The horizontal dotted line is set at 90%, and the vertical lines show the shift size that each QC plan can reliably detect, that is with 90% reliability. For example, a QC plan with 2 repeats can reliably detect a shift of 3 standard deviations. So using that example, we ask, what testing processes have critical shift sizes that are greater than 3 standard deviations? So our general criteria for controllability is that the critical shift size has to be bigger than the shift size that a QC plan can reliably detect. This is shown in line 1, just written out in words. The idea is expressed mathematically in line 2 using symbols. And we just got the number from the power chart and found that 90% reliability for a repeat of 2 controls using the 3SD rule, that we can reliably detect a shift of about 3 standard deviations. So we have a value for the right-hand side of line 3. Well, we can use our definition of the critical shift and substitute that in, as shown on the left-hand side of line 4. Then we do some algebra, and you get the equation in line 5. As you can see, this is a straight line with a y-intercept or vertical intercept of 1 and a slope of minus delta s plus z. So this is nice. This is exactly the line that we saw associated with a QC line on the OPSpec chart. This line defines the controllable region for this particular QC rule. So the big picture is that QC rules define a controllable region in the operating plane. A QC rule can control a process operating at a particular operating point if the operating point is in the controllable region. And now we've seen how to find that line. So we've covered a lot of ground here, and you're probably asking, what do I really need to know? And I would say that the key thing is how to use an OPSpec chart. How to plot your operating point and how to select a QC rule. The other items are nice to know, but not absolutely necessary. In my opinion, it's always good to understand the assumptions behind a method when you use it, but it's not absolutely essential to use it. So what don't you need to know? You don't need to know how to create a power chart. You should be familiar with them and know what they mean and know that they're connected to an OPSpec chart, but you don't need to be able to make them. And you don't need to be able to make an OPSpec chart. You just need to be able to use it. You should now have a good understanding of all the pieces of this diagram. This is our bird's eye view of the overall QC process. In the final video, I'll provide a roadmap for QC optimization, or the war on variation. The first step is to stabilize the process. And once the process is stabilized, you can evaluate process capability. And as you remember, process capability describes the risk associated with the process when it's in control. That is, the probability of producing serious errors. We can evaluate this risk and determine whether it's acceptable. If it isn't acceptable, we need to reduce variance. So once the process is capable, we can then ask, will we be able to detect a change when the process goes out of control? So we evaluate risk in 2 conditions. When the process is in control, and that's capability, and out of control, when we look at QC plans to guarantee that we can detect a shift that would produce unacceptable results. And the final step is to improve the process. We improve the process by reducing variance. Reducing variance increases capability and controllability, and this in turn reduces costs and improves patient care. So by now you're, I'm sure, tired of this, but once again, looking at our bird's eye view diagram, quality control rests on 3 fundamental concepts: stability, capability, and controllability. Okay, that's it for this video. I'm sorry it's so long, but to quote Winston Churchill, I didn't have time to make it short. I hope you find this useful. Please contact me if you have any questions or you'd like to talk about anything I presented. And thank you for listening.